Hey there, Calc BC kids. Today we're going to be looking at integration using partial fractions, something we've attempted before, and some of you used a calculator that we had utilized online. But consider the fact that when we want to find the antiderivative of this particular function, the integral of 2x plus 4 over x squared dx, and think for a moment how you would solve this. Okay, so now that you thought for a moment, then you thought, oh, well, I'll probably just split the integral, right? So I would probably just say, okay, that's going to be 2x over x squared plus 4 over x squared dx. And then I would just give it a shot and say that, okay, that's going to be the integral of 2x to the negative 1 dx. And then plus, then I would split it as 4 x to the negative 2 dx, and I would then integrate, and I would get 2 times ln of the absolute value of x and minus 4 over 3x cubed, and then that would be plus the arbitrary constant c. Okay, so easily integrable once we manipulate it. Now, what did you have to do to the expression in order to find this? You had to split the fraction, right? Split the fraction. So that can be done when you have a sum or a difference over the denominator. So you can split the numerator, I guess, is really what I wanted to say. But okay, so consider this expression. Okay, so consider the expression 2 over x minus 4. And if you had to find a common denominator, you know you would find the LCD first would be equal to the product of their distinct denominators. Okay, so we have that. Now, so if I have 2 over x minus 4, x minus 4, I'm going to leave a little space, plus 1 over x plus 2, then I'm going to get a common denominator by multiplying the first fraction by the missing factor of the LCD, x plus 2 over x plus 2. That's not going to be too sloppy. And then for the 1 over x plus 2, I'm going to multiply that by the missing factor for that fraction, x minus 4 over x minus 4. So then what I'm going to do is I'm going to multiply, and you know this, 2x plus 4 plus x minus 4. So there's the numerator, and then the denominator would be x minus 4. Got to watch out with this, putting parentheses around, making sure that you multiply properly, over x plus 2. So the numerator then becomes 3x over the denominator. And we could easily multiply that together, x squared minus 2x minus 8. So now think about it for a second. If we had the integral of 2 over x minus 4 plus 1 over x plus 2 versus, now you know that's kind of easily handled, right? So suppose that you wanted to find out the antiderivative of this expression. Which form would you use? Would you use 2 over that, so boom, like this, put a dx on the end? Or would you do this 3x over x squared minus 2x minus 8 dx? So even looking at what I had in the beginning, if I had to integrate it, you know that that's just natural logs, right? So kind of a nice setup there, right? So consider the ratio of two polynomials where the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. Then the fraction can be broken into partial fractions based on the factors of the denominator. So if we let n of x represent the numerator and d of x represent the denominator, where the degree of n of x is less than the degree of d of x, We have 4 possible cases to consider when using this procedure. However, we will not be considering all of them. I'm just going to let you know, hey, this is out there. So case 1, where you have the degree of the numerator, n of x, and the degree of the denominator. Okay, so not especially the degree, just the setup. So now what I do with this, instead of A1, A2, is I usually just say that's A, this is B, and this is C, or whatever letter they are until we stop. Where we have distinct linear factors, that means unique linear factors in the denominator. Okay, so that's case 1. Case 2 is going to occur when the denominator contains a non-factorable quadratic factor. So what we're going to do then is we're going to have this ax plus, oh, sorry, not capital there. My mistake, because we're using them in the denominator. So you can see we have ax plus b. So what we're going to use is a linear when it's a non-factorable quadratic, such as, consider that if your denominator was something like x squared plus 1. It's not factorable over the real numbers, though it is with the imaginary numbers. We're dealing with functions in the real plane here. Okay, case 3, when we have repeated linear factors. So now if you look at the numerator is a polynomial, the denominator is x minus a to the nth power. So if you're looking and you have this situation, then with repeated linear factors, I'm going to say a over x minus a, lowercase a, b over x minus a squared, and we're going to keep using a different constant until we reach the highest power of n, and you can see that that's on this last term. Okay, and then you have a 4th case where you have repeated non-factorable quadratic factors. So this is going to kind of look like repeated linear factors, but you can see where we have a 2nd degree all the way up to an nth degree to match the n that you have in the denominator with n factors of that non-factorable quadratic. Okay, so we're going to start off with, let's go back here to case 1 where we have distinct linear factors. And this is the type this is a type that is tested on the AP exam. So here we go. All we're going to do here is work with a partial fraction. So this is the method. This is one of the methods. There are a couple, but I'll go over the first one, the one that seems kind of easiest for students. So we have this fraction x over x squared minus x minus 6, and we're going to say that this is equal to an a. Oh, first, let's factor this. We have x, this is equal to, I'm going to watch the space that I'm going to use here, put that up here. So I'm looking at the denominator, and I can see that the factors of the denominator are going to be x minus 3. And so I'm going to put an a over x minus 3, and then I'm going to put a b over x plus 2. So what I've done is I looked at the denominator and I'm saying, well, this is x over the quantity x minus 3 times x plus 2. Okay, so then that means those are the 2 linear factors for the right-hand side. And I think instead of this, I think I'm going to put x minus 3 here and x plus 2. So now what I'm going to do is multiply both sides of this equation. So I'm going to multiply by the LCD, which is x minus 3 times x plus 2. So on the left-hand side, you're just going to get the numerator, which is just x, is equal to, on the right-hand side, you're going to get a times x plus 2 plus b times x minus 3. And you can, if you want to take the extra step to resolve that with yourself, then do that. But remember that you're multiplying by the LCD, and certain factors will cancel when you do that. Let me just do a for instance here. Like if I multiply by x minus 3 times x plus 2, here I'm going to multiply by x minus 3 times x plus 2. So you can see that here the x minus 3's will cancel. Here the x plus 2's will cancel. Okay, go back just a few steps here. Okay, so now we have this equation, right? Now, this is kind of a cute little method. When I first saw it, I thought, wow, okay, it goes pretty easily. So now what you're going to use, so here's our first step here. And then the second one, we're going to use excluded values. So now think of this fraction in the beginning, and then which values would be considered excluded values. So we're going to use x is equal to 3 and negative 2. So we're going to say x is equal to negative 2 first. So we're going to plug in here. So we get negative 2 in for x. We get a times negative 2 plus 2 plus b times negative 2 minus 3. So you can see that this is going to go to 0. And so you're left with negative 2 is equal to negative 5b. So that tells us that our b value is equal to 2/5. Now, one of the things I do initially is I'm pretty careful about my coefficients in the beginning. It's easy to get a and b mixed up. Whenever you have two things, heads or tails, if you're not careful, it's easy to get them mixed up. Okay, so b is equal to 2/5. So then I'm going to take the other x value, the other excluded value. I'm going to plug that in. So I have 3 is equal to, now I'm going back to this equation up here. So I've got a times 3 plus 2 plus b times 3 minus 3. You can see that the second term is going to go to 0. So we're left with 3 is equal to 5a. And then we're going to take that, we're going to get a is equal to 3/5. Okay, so now I've got, and all we're doing is decomposing the fraction. So here I can say that a is 3/5, so I can say that x is over x squared minus x minus 6 is equal to 3/5 over, that's your a, over x minus 3, and then plus 2/5 over x plus 2. Now, you might wonder why I leave it as a fraction in the numerator. You're going to be dealing with logarithms, and you can easily take a fraction and throw it out in front of the integral, so I think it's very handy to just leave it like that. But 6 of one, half a dozen of the other. Okay, so now taking this, so we're going to find the antiderivative of this. So we have the integral of 3/5 over x minus 3 dx, and plus, I think I had left it originally just like this, so I'm going to leave it like that, 2/5 over x plus 2 So I end up going to pass the 3/5 out, and I get ln of the absolute value of x minus 3 plus 2/5 times ln of the absolute value of x plus 2 plus c, the arbitrary constant in there. You have it. There it is. Okay. All right. Let's look at the next one. So the next one is a little longer, so I'm going to take the time to go through this. We're going to set this up. We have negative x squared plus 3x plus 29, and that's all over and I have this in factored form already. X plus 1, and then I have x minus 4, the quantity squared. So I know that this is going to be an a over x plus 1 plus it's going to be b over x minus 4. So now we have repeated linear factors, so it's going to be c over x minus 4, and then that's going to be squared. Okay, now then I'm going to do that first step where I multiply by the LCD. In this case, it's x, what you see in the denominator here. So when we do, then we're going to get negative x squared plus 3x plus 29 is equal to, now you got to be careful when you do this. Remember, you're multiplying by the LCD. Everything gets multiplied. Each term gets multiplied by x plus 1 times x minus 4 squared. So what you're going to get then is a times x minus 4 squared plus b times x plus 1 times that extra x minus 4 plus c times x plus 1, because both of the x minus 4's cancel. Okay, so now what we're going to do the same thing where we're going to plug in the excluded values. So my second step, let me tell you what, let's put a little bit smaller here. Okay, so the second step then, we're going to use the excluded values. There's the first step there. So we're going to start off with x is equal to, maybe put it over here, x is equal to negative 1, because that's where the x plus 1 will equal 0. So we get then negative 1, negative of negative 1 squared, plus negative 3 plus 29 is going to be 25. So when I put this in, a times negative 1 minus 4 squared plus b times the quantity negative 1 plus 1 times negative 1 minus 4, and then we have plus c times negative 1 plus 1. So it turns out, is there a pen here? We get 25 is equal to, we get negative 20, we get 25a, and then as it turns out, then this term goes to 0 and this term goes to 0. So we get 25 is equal to 25a, leaving us with a is equal to 1. Okay, then I've got x is equal to, pull this in here a little closer since I didn't really use that. So now I've got x is equal to 4. So on the left-hand side, as I put that in, I got negative 4 squared. Negative 4 squared plus 3 times 4 plus, that's 12, negative 16 plus 12 plus 29. So it'll be negative 16 plus 12. It's going to be negative 4 plus 29 is 25. So again, you get 25, just a coincidence. And then for the first factor, we're going to get a times 4 minus 4 squared plus b times 4 plus 1 times 4 minus 4 plus c times 4 plus 1. Okay, simplifying this, we've got the first term goes to 0 and the second term goes to 0. So then we are left with 5c. 25 is equal to 5c. So it turns out c is equal to 5. C is equal to 5. And now, so we have A, we have C, but we need to get B. So we choose an arbitrary number that is not excluded, but it gives us what we want. So we're going to plug that into the polynomial here. And so if I plug that into the left-hand side, we get 29. So we get 29 is equal to, so then I'm going to say A is 1. So I'm going to plug that 1 in for A, and then it's going to be 0 minus 4, the quantity squared, plus, then I have B that I don't know yet, B times 0 plus 1, and 0 minus 4, plus we have C times 0 plus 1. But C, the C value is 5. It's a fat one here. Let me try that. So I'll put the 5 value in for that C. So then I have C times 0 plus 1. Okay, so I get 29 on the left-hand side is equal to 1 times negative 4 squared, which is going to be 1 times 16, which is 16. And then for the B, I'm going to get negative 4B. So I'll put that as minus 4B. And then I get plus 5. So I get 29 is equal to 21 minus 4B. Or I get 8. 8 is equal to negative 4B. And it turns out that B is equal to negative 2. So now I have A, B, and I have C. So then let's set this up. Here's our original problem. Again, being careful when you set this up. So remember what you're doing. You're finding the integral, and I'm going to put this in as star. So I'm going to say star is now equal to the integral of A over, so it's going to be 1 over x plus 1 dx. Here, let me make this all one integral. And then B is negative 2, so I'm going to make that minus 2 over x minus 4. And then plus C is 5, so that'll be 5 over x minus 4, the quantity squared. So then my answer is ln of the absolute value x plus 1, just a natural log, minus 2 times ln of the absolute value of x minus 4. And then I've got a real simple u sub, but it's going to be a minus 5 over x minus 4. We raise the power 1. And what else do we have? And plus C. Let me just think for a moment about this. 5 is negative 1 over negative 1. Got it. Okay. And here's your answer then. Okay. So easily integrable then. Boom. Okay, so that would be your original integral. Sometimes I'll do that where I don't want to write the whole thing, but I'll put a little star just to kind of pick up. All right, let's try one more. So for the next one, we want to find the antiderivative. Again, we're dealing with distinct linear factors or repeated factors. So with this one, where we've got the 4x squared over, we've got the denominator that I want to go ahead and factor. So with that, I'm going to group. So I've got x cubed plus x squared. I'm going to group those together, and then I've got a plus, and I've got a negative x minus 1. So I'm going to factor out the x squared, leaving me with x plus 1. And I'm going to say plus a negative 1, which will leave me with an x plus 1. I'm going to factor out the x plus 1. When I factor out the x plus 1, it leaves me with an x squared minus 1. I would continue to factor it then as x plus 1 times x plus 1 times x minus 1. And then we have our factored form. So with the factoring that you have there, then we've got x plus 1, the quantity squared, times x minus 1. So I'm going to put that factoring here. Put the x minus 1 first, and then I'll put the x plus 1, the quantity squared. Okay, and you don't think I really need the factoring here, so I'm going to get rid of that. And then I'm going to set up, I've got one linear factor, so that's going to be a over x minus 1 plus b over x plus 1 plus c over the repeated linear factor x plus 1 squared. Okay, so I get 4x squared because now we're going to multiply by the LCD. So when we do, we get 4x squared is equal to. So remember, you're multiplying both sides of this equation by x minus 1 times x plus 1 squared. So when you do, you're going to get a times x plus 1 squared plus b times x minus 1 times x plus 1 plus c times x minus 1. Using your excluded values, we'll use x is equal to 1. So we get 4 is equal to, if x is going to be equal to 1, we get a times 2 squared, or 1 plus 1, I'll put it in squared, plus b times 1 minus 1, which is going to be 0, 1 plus 1. So that middle term is going to go away to 0. And then we've got plus c times 1 minus 1. And that will also go to 0. So then you end up with, you have 4 is equal to 4a. So we have a is equal to 1. Okay. Then we use our next excluded value, x is equal to negative 1. So we get 4 times negative 1 squared, which is still 4. 4 is equal to, then we have a, which is 1. We could put the 1 in there. I'm going to leave it because it's just going to be a times negative 1 plus 1 squared. And then I have b times negative 1 minus 1 times negative 1 plus 1. And then I have c times negative 1 minus 1. So the first two terms, this one goes to 0, and that product goes to 0 as well. So I end up with 4. 4 is equal to negative 2c. So we get a c value that's equal to negative 2. Here's our c value. And then we've got to choose another. So I'm going to choose x equal to 0. So I've got 4 times 0, which 0 squared, which is still going to be 0, is equal to. So I get a times 0 plus 1 squared. Now in this case, a is going to be 1, so I'm going to plug that in. I'm going to make our job a little bit easier here. 1, a, then times 0 plus 1 squared, plus, we don't know b yet, so b times 0 minus 1 times 0 plus 1, plus c. C we know is negative 2, so we can put that in. And we have 0 minus 1. So for this one, what do we get? We get 0 is equal to, here we get 1 plus negative b, or we could just say minus b, plus minus b, and then it's going to be plus 2. So then it looks like b is going to turn out to be equal to 3. B is going to be 3. Okay, now I've taken quite a bit of the space up here, so what I'm going to do is scrunch this and make it smaller. So we multiply by the LCD, and then used excluded values. And now, so we get the following. We have all of our values, a, b, and c. You just have to be very careful so when you're inputting them. So we get the star here is equal to. So here we go. The integral of 1a over x minus 1. And then I have plus 3, b is 3, over x plus 1. And then I have plus c, which is negative 2, so we'll make that a minus 2 over x plus 1, the quantity squared, dx. So when we multiply that, we don't multiply it, when we integrate that, then